the first derivative. So the first derivative, we need to know the definition behind it. And the definition of the first derivative is that it's the gradient of the tangent at any given point. So remember, our first derivative always gives us the gradient of a tangent. So let's draw a curve. And let's see what's happening along this curve. So over here, if we were to draw tangents along any of these points, those tangents would have a positive gradient. So let's mark those in. So we'd know tangents would have a positive gradient all along here. If we drew a tangent right at the top here, its gradient would be 0. If we drew tangents anywhere along here, we'd know they'd all have negative gradients. Positive gradients over here, and back to negative gradients over here, and we'd have a 0 gradient there, and a 0 gradient there. Now let's learn some definitions. Whenever a function has a positive gradient of the tangent, we say the function is increasing. Whenever it has a negative gradient of the tangent, we say the function is decreasing. And whenever the gradient of the tangent is 0, we say it's stationary. So, in mathematical terms, it's increasing when our first derivative is greater than 0. It's decreasing when our first derivative is less than 0, and it's stationary when our first derivative equals 0. Now with our stationary points, so we can see they're single points, whereas increasing and decreasing parts are on numerous points. We can have a few types of stationary points. One here, we actually call it a maximum turning point. So turning point and stationary point are similar. So we call this one up here maximum turning point. And one like this, we call a minimum turning point. So we can have two other types of stationary points, which will look something like this. One will look like that, very similar to our cubic function. And another one will look like that, where right in the middle there, the gradient is actually 0. And both of those are called horizontal points of inflection. Now, what's the difference between all of these turning points? Well, the difference is what's happening on either side of those turning points. On the maximum turning point, you can see that we have positive gradients, then a 0 gradient, then a negative gradient. So maximum turning points have positive gradient, they have a positive gradient, then a 0 gradient, then a negative gradient. A minimum turning point has a negative gradient, then a zero gradient, then a positive gradient. So we can see negative going to a zero to a positive. And our horizontal points of inflection, these stationary points, well, this one up here goes from a positive gradient to a zero gradient to a positive gradient. So this one here goes from positive to zero to positive. And this one goes from a negative gradient to a zero gradient to a negative gradient. So negative, zero to negative. So they're the four kinds of stationary points we can have on our curve. And the thing in common with all of them is that the first derivative will equal zero at the turning point, or at the stationary point. So let's have a look at an example on how we can use our first derivative to give us information about our curve. So now we're going to have a look at an example how we can use the first derivative to tell us information about the graph. So we're going to look at y equals x minus 7 times x squared minus 5. Expanded, that's going to give us x cubed minus 7x squared minus 5x plus 35. I'm going to graph this out just so we can see what's going on as we do the question. But essentially we'd actually be just given this equation and using the first derivative we would actually graph it, but I want us to see the graph so we can see what's going on. So we'd actually have intercepts at 7, root 5 and minus root 5. Not expected to know how to do this, just I just want to show you what's going on. And we get something like that. And we're actually going to use the first derivative to show us where the stationary points actually would be. So we know that they're going to be there and there, but we're going to use the first derivative to do that. So let's go ahead and find the first derivative of the expanded form. So we get 3x squared minus 14x minus 5. And we just learned that for stationary points, the first derivative equals 0 for stationary points. So we can go ahead and say, it should be part of the working out. And then we can say that, well, 3x squared minus 14x minus 5 would equal 0, and that's where our state, and we just have to solve this for x to figure out where our x coordinates of the stationary points are going to be. So we can factorize this quadratic. We're expecting two answers because we've got a quadratic equation here. So this is the way I like to factorize a quadratic. We'll multiply these together, get minus 15. So we're looking, so because it's 3x squared, I write 3x all over 3, multiply by the coefficient of x squared by the constant to give us minus 15. And we're looking for two numbers that multiply to minus 15 and add up to minus 14. So that'll be minus 15 and plus 1. We can factorize out a 3. So we'll get 3 outside of x minus 5, outside of 3x plus 1, all over 3, and the 3's will cancel out. And now we can solve this so that x would equal minus a third and 5. And that looks like it makes sense because that could be the minus a third and this could definitely be the 5. So that's what's happening as we're solving here. So here we get minus a third, and here we've got a value of 5. But remember, you won't have the graph as you go. We're meant to do this to be able to get the graph, but we just want to visualize what's happening as we go. So remember, we're after a stationary point, so we need the y values for these. So we can just go ahead and sub the x values into our original equation. Either of these, they're both the original equation. I'm going to go ahead and sub it into the factorized form. So this is for the y coordinate. So when x equals minus a third, we're going to sub it into y. So we get y equals minus a third minus 7 outside of minus a third squared minus 5. And all that in the calculator is going to give us 968 over 27, which is about 35.85 to 2 decimal places, just so we know where it lies on the graph. And when we sub in x equals 5, we get y equals 5 minus 7 outside of 5 squared minus 5, and that would give us minus 40 for our y value. So what's happening there is that when we have x is minus a third, we're getting a y value of 968 over 27, and when we sub in 5, we're getting a y value of minus 40. Okay, so now we can say we have stationary points at minus a third and 968 over 27 and 5 minus 40. But what kind of stationary points do we have? Well, we know because we can see, but how can we use the first derivative to help us? And to do that, we actually make little tables. And we're going to analyze what's happening on either side of our stationary point. So we're going to make a table using the x value and the first derivative. For each of our stationary points, we need to do this. So we're looking at our x value and the first derivative. And right in the middle, we're going to use our first stationary point for each one. So we want to see what's happening on either side of these points, because remember, the first derivative is the gradient of the tangent. And if we're looking on either side and we know we have a positive gradient on the left and a negative gradient on the right, we've got a maximum turning point. And if we know if we've got a negative gradient on the left and a positive gradient on the right, we've got a minimum turning point. So we know if we sub in minus a third into the first derivative, we get 0, because that's how we got it in the first place, and the same goes for 5. And we want to check what's happening on either side. So we take a little bit to the left of minus 3, so we can use minus 1. A little bit on the right of minus a third, which is 0. A little bit on the left of 5 would be 4. And a little bit on the left, on the right of 5 would be 6. So subbing, all we need to do now is sub in these values into our first derivative and see what we get. So subbing in minus 1 into our first derivative is all the way up here. We want to sub minus 1 in. I'm just going to do that up here. So let's sub in minus 1. So we get 3 times minus 1 squared minus 14 times minus 1 minus 5. So we get 3 plus 14 minus 5. And we're going to get 13. We're going to get 13. Put it in red. So we're going to get 12, sorry. So we get 12. So we can put that in here. We know we get 12. If we do the rest for the other values, subbing in 0 would give us minus 5. If we subbed in 4, we'd get minus 13. And if we subbed in 6, we'd get 19. So essentially what we've got is we know on the left of the minus third, we've got a positive gradient, and on the right of the minus third, we've got a negative gradient. So if we just represent that with a little diagram, so positive gradient, then a zero gradient, then a negative gradient, you can see that this one's a maximum turning point. And here, if we have a negative gradient, then a zero gradient, then a positive gradient, we get a minimum turning point. So this is how we can use our first derivative to firstly find a stationary point and then check the nature of the stationary point, whether it's a maximum, minimum, or horizontal point of inflection.